Okay. First thing we're going to do is we're going to look at this quick review before the new. I should have already done that one. So we know variables can either be quantitative or categorical. If you went through these, this is quantitative because it's number. The type, like a dog, a cat, that's categorical. Number, quantitative. Grade point average, quantitative. Hair color, just categorical. And then it says a random variable is either discrete or continuous. It's already a number, so it's already quantitative. So that number can either be discrete or continuous. Remember, discrete is like whole numbers. Continuous is that it takes on a decimal or a fraction. Classify the following distribution. So using these answers up here. So normal is a continuous random variable. Binomial and geometric are both discrete. Number of articles randomly chosen in a paper, discrete. Amount of time, continuous. Number of shoes, discrete. Number of classes, discrete. The volume of water, continuous. So those two right there can take on decimals or fractions. From chapter 9, the null hypothesis is the statement of no difference. The alternative hypothesis is what we're trying to find evidence for, though. For this multiple choice here, you can see I kind of went through the different possibilities there. Like here it says the number of the number of students from Central High School was 10 greater than the number of students from Liberty High School. So there was 100 from Liberty and 60 from Central High, so I just kind of figured out the 4 years. So I took the 20 and the 0.3, so that's not true. At Liberty High School, more students selected a four-year university than any other activity. So Liberty High School, that is not true. Obviously, this bar is higher. For the category join the workforce, the number of students from each school was equal. So yes, the proportions are equal, but the numbers are not equal because they didn't talk to the same sample size. Then the last one, the same number of students selected a four-year university in the military. For Central High School, that's clearly not true. This proportion is higher. And then for the category undecided, the number of students from Liberty High School was 4 greater than the number of students from Central High School. So if I take that 0.10 times 100 and 0.10 times 60, that one's the one that works. All right, in this particular chapter, we're still sticking with significance tests. We're not going to do any confidence intervals. We're also going to work with a categorical variable, but we are going to use a new distribution. It's called the chi-squared distribution. Those of you who've taken AP Bio, you might be a little bit familiar with this one already. So a one-way table, we've seen this before. A one-way table just has one categorical variable. We saw that back in chapter 1. And a chi-squared goodness of fit test, and this is what you do in AP Bio, it's trying to figure out how well does the data fit a hypothetical or hypothesized distribution. So M&Ms, if I take a sample of M&Ms, how well does that fit the data, my sample fit what I would expect from the M&Ms? Your null and alternative hypotheses, you can write them a couple ways. Page 685 in the book kind of shows us how the HO says it's going to be equal to some proposed distribution. So you might be saying that all the proportions are the same, or you might be saying that the proportions are equal to some certain percent. The alternative says that at least one of them is different. When we calculate the expected counts for a chi-squared, we're calculating the expected counts under the assumption that the null hypothesis is true. Do you round these to the nearest integer? No, because they're just an expected count. The chi-squared test statistic looks like this. It's chi-squared. There's our summation. You take the observed value minus the expected value. Those are squared. We divide it by the expected. When we do that calculation, then we add them all up. It is in the formula sheet. And it measures how much different, so it's a ratio of how different the observed value is from the hypothesized or the expected value, okay? The sampling distribution of the chi-squared statistics, when we calculate this value does not follow a normal distribution. It follows a right-skewed distribution that only allows for positive values. If it were normal, it could be positive or negative. So this one only allows for positive values. When you square it, you can never get a negative value there. So it's not a normal distribution, it's a new distribution. The chi-squared distribution is a family of distributions. And a particular chi-squared distribution is specified by giving its degrees of freedom. So we've seen this before. To know which curve you're using, you have to calculate the degrees of freedom. Depending on what test you're doing, the degrees of freedom are a little bit different. The chi-squared goodness of fit test uses the chi-squared distribution with degrees of freedom equals the number of categories minus 1. So we have to figure out how many categories we have, and then we subtract 1 from that. And here's the picture here. So these are some possible shapes like your chi-squared distribution could have. So when the degrees of freedom are low, there's a, well, let me show you this other app here. So if the degrees of freedom are low, so this one, it's very right skewed, looks somewhat exponential. As I change the degrees of freedom, as I increase them, it's still right skewed, but you can see it's starting to smooth out a little bit. Does it start to look like a normal curve at some point? Sure, but it's its own distribution. It's the chi-square distribution. It does have its own like function, but this one is just, it's pretty much going to be right skewed for a while. At a certain point, you know, maybe it'll start to look more normal, but it is it's its own distribution. So don't try to use the normal curve for the chi-squared problems. Okay. All right. So next up here, since we are doing these just significance tests here, we're not doing any confidence intervals. We might have to find that p-value. Yes, there is a calculator command, but on some of the calculators it's not available. So if you had to find the calculator, if you have to find the p-value, just like we had a normal CDF and just like we have a t-CDF, we also have a chi-squared CDF. So the chi-squared CDF, it's always the lower bound, comma the upper bound, comma the degrees of freedom. When we're running these significance tests, what happens with these significance tests is whenever we find that p-value, it'll always end up being in the right tail. If the values are, so remember this is 0 and the numbers can only get bigger this direction. So if the values were exactly the same, so if the, remember it's the observed minus the expected squared over the expected, and then we add them all up. If these observed and expected are exactly the same, we would expect, you know, that calculation, that chi-squared value, when we find it, it's going to be close to 0 if the observed. So then when we find the p-value, we're always finding the area in the right tail. If these values start to get further apart, then we're going to see that chi-squared value out here, so the p-value is going to start to get smaller, so it's going to make us more likely to reject our null. All right, so let's say we wanted to find, so that what I'm trying to say here is that the upper bound is always going to be a positive infinity. And right now we're using the degrees of freedom. I think the book uses k minus 1 for the number of categories minus 1. So in this one, if your chi-squared test statistic, we want to find the p-value. If the chi-squared value is 10 and the number of categories is 16, that would mean my degrees of freedom would be 16 minus 1. So what I would do here is I would take, so I'd go to second vars, whereas all my other ones are. There's a chi-squared PDF and a CDF. Chi-squared is a continuous distribution, so the PDF just tells you a point on the curve. We always want to use the continuous one, so we're always using the CDF. So I'd have chi-squared CDF. My lower bound will be that 10. My upper bound will be positive infinity. When you're using that E, don't forget to use that E from the second comma. And then the degrees of freedom are going to be the 15 that we had up here. So when I hit all that there, I get a pretty high number here, okay? Because if my degrees of freedom are 15, I'm not quite as skewed. This one, I have a chi-squared value of 35 and a number of categories of 25. So again, I'm going to find that degrees of freedom. And I'm going to do 35, E99, and then I have 24. So I put paste there, and I get that value right there. So again, I did 35, E99, 24. Okay. All right. So again, we're just doing significance tests here, so we're not worried about the confidence interval. So we have our state, so what hypotheses do you want to test and at what significance level? Define any parameters. Sometimes these ones we can write out in words and we won't have to define anything. I'll show you two ways to do them. plan. So identify the appropriate inference method. Check your conditions. We have random, large sample size, and independent. We don't have the normal check here. We don't think this statistic here does not follow the normal curve. This statistic follows the chi-squared. So this check is a little bit different. The random checkers are familiar. Is it random? Is it a random sample or is it a random assignment? The large samples, like I said, there's no normal check here. What we want for the large samples is we want to make sure our expected counts are at least 5. It's the expected counts. I don't care about the observed counts. I just want to make sure that the expected counts are at least 5. Then it says here that the sampling distribution of the chi-squared statistic is close to a chi-squared distribution with the degrees of freedom equal to the number of categories minus 1. So what that's saying here is that if these expected counts are 5, then this should follow that chi-squared shape. Independent looks the same. Either we did random assignment or we took a sample without replacement and then we're checking the 10% condition. Here's the test statistic. There is a calculator command, but it's not on the older calculator, so I'll show you both ways when I go through the first example. Interpret results. So if you're given a significance level, compare your p-value to alpha. If you're, sorry, some of this got cut off here. If you're not given a significance level, then pick one in step 1. State if you're rejecting or failing to reject, and then write your final piece in reference to HA. I didn't change any of this. This looks the same as it looked in all of our chapters. All right, in this problem here, so this one says, Malcolm, so in his book Outliers, Malcolm Gladwell suggests that a hockey player's birth month has a big influence on his chance to make it to the highest levels of the game. Specifically, since January 1st is the cutoff date for youth leagues in Canada, where many NHL players come from, players born in January will be competing against players up to 12 months younger. The older players tend to be bigger, stronger, and more coordinated, and hence get more playing time, more coaching, and have a better chance of being successful. To see if this is true, a random sample of 80 National Hockey League players from the 2009 to 2010 season was selected and their birthdays were recorded. Overall, 32 were born in the first quarter of the year, 20 in the second quarter, 16 in the third quarter, and 12 in the fourth quarter. Do these data provide convincing evidence that the birthday of NHL players are not uniformly distributed throughout the year? Uniformly means that they are all equal to each other, okay? So this one says the birthdays of NHL players are uniformly distributed across the quarters. So my null hypothesis is just saying that they're equal. So it's like I'm saying the other way we could write this null hypothesis is that we can say that the P1 is equal to P2, equal to P3, equal to P4, which is all equal to 1/4. And those P's, those different P's, so I wrote P number, is the true proportion of births in that quarter. So P1 would be the true proportion of births in quarter 1. P2 would be the true proportion of births in quarter 2, and so on. I'm setting it equal to 1/4 because there's 4 of them, so to make them uniformly distributed, they'd all have to be 1/4. If you're going to write your null like this, then the alternative is going to say at least one of the P's is incorrect. So at least one of these is wrong, which obviously will make 2 of them wrong. If we're writing it out in words, then what I kind of do here is basically I'd be saying that the birthdays of NHL players are not uniformly distributed across the quarters. So I just kind of use the ditto marks and say not uniformly distributed. And, dot, 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 obviously. Okay. So my do step. So this is a chi-squared goodness of fit. The random, it says that they took a random sample. All right, so we don't have a normal check here. We have this large sample check here. So we want to check our expected counts. So the expected counts here. So basically, if I take that 80 So my null hypothesis, remember I find the expected accounts assuming the null hypothesis is true. So I take that 80 and I'd have to split it up amongst the 4 quarters. So there's 20 in at least quarters, so those are at least 5, so my condition's been met then. My independent, we took a sample without replacement, so I'm going to check my 10%. Forgot a part there. I'm going to check my 10%. Fortunately for us, there were 879 NHL hockey players in that year. All right, when we do our test statistics, so again, we're adding up several things here, but it's always the observed minus the expected. So the observed for the first quarter is that 32. So it's the 32 minus the expected. So again, my expected was 20. It would be squared over the expected. And then I would have the second one. So it's 20 minus the 20 squared all over the 20. And then I'd have my third one. And then I would have my fourth one. And then I would calculate that. All right, so you could do all that by hand. I'm going to show you 2 ways to do it in the calculator. Both ways I show you, you're still going to have something in list 1 and list 2. So the one way we could do it, so I'm going to type my observed in list 1. So I've got my 32, my 20, my 16, and then my 12. And I'm going to put my expected in list 2. So then I'm going to use list 3 to do the math for me. So if you notice here, I put my cursor up there. I use my up arrow, black box. I'm going to press enter. Cursor's blinking down here. So I'm going to say observed, which are in L1, minus the expected, which are in L2, divided by the expected. And then what I'm going to want to do, I feel like I did something. No, I didn't do anything wrong. I did do something wrong, right? Let's clear that. We're going to do that again. Ready? I got to have my observed minus my expected, and I have to square it. Then I'm going to divide it by the expected. So the observed are in list 1, expected are in list 2. I got to square it. I was like, there's something totally wrong here. All right. What I need to do is I need to add up those numbers. It's because those are these individual components here. Sometimes you'll be asked to do a follow-up analysis when you're doing a chi-squared test. And when you're doing a follow-up analysis, you're trying to figure out which one of these terms or components has the biggest influence in the final answer. If you look here, I can see that first quarter has the largest influence because of that 7.2 is going to make this result large. All right, so like I said, I need to add those up. So you can either memorize the numbers or you can go back here and go to second stat, go over to math, go to number 5, and add up everything in list 3. And we get 11.2. And then when I want to find my p-value, so I'm going to go second bars, I would have 11.2, E99. There's 4 categories here because I have 4 quarters. So I'm going to do 4 minus 1, and I'll get my 3, and I'd hit paste. And I'm going to write down here, there's my p-value. So I'm going to write p-value. So it's equal to this. My degrees of freedom were 3. They didn't give me a significance level in this problem, so I'll just back up here, state that I'm going to use my default here. So I can say here the p-value is less than alpha. So if I'm less than alpha, I'm going to reject HO. And if I'm rejecting HO, then I can say there is enough evidence to say, and again, we want that context here, the birthdays of the NHL players are not uniformly distributed. Okay, couple things. So like I said, there's another way we could find these answers. So the other way we can find these answers is when you go to stat and you go over to tests. On these newer calculators, there's a chi-square GOF test. So you still have to have your observed in list 1, and you still have to have your expected in list 2. And then the degrees of freedom, you're going to have to change that. The color is only if you want to draw it. Then, and then we'd hit calculate. And if you notice there's my answer. There's my p-value. There's my degrees of freedom. And then those pieces are my contributions, it's called. So that's the contributions. And again, those are those individual components there. All right, so those are those individual pieces from the chi-squared test statistic. Now, back up here, I wrote out everything. Honestly, I would not expect you to write down all 3 of those terms. So usually what my expectation is that you just write out the first one, and you can do plus and then dot, 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 and just give me the answer. You don't have to write out every single term. You can, but you don't have to. All right, when should you do a follow-up analysis? So again, you really are only going to do one if you reject HO and if you're asked to do one. So you don't have to do one if you're not. How do you do it? So you just look at that contribution there. So look at that CNTRB list, or look at your list 3. You're just trying to figure out which one is the biggest contributor. So with Gladwell here, my follow-up analysis would say, I could say that it appears Gladwell is correct. Actually, let me not. So the follow-up analysis, I'll comment on that in a second. So the follow-up analysis, I would just say that the first quarter is having the largest contribution to the test statistic. And then, so it's having the largest contribution to the test statistic. What I was going to write here, which I'll comment on right now, is that his suggestion was that hockey players' birth month has a big influence, and so he felt that the players born in January, they were more likely to have players born in January. So based on this, it does appear that he was correct, because that first quarter is having the most influence on everything. It appears that he was correct in his thinking that players born early in the year are more successful in the NHL. With the follow-up analysis, all you're doing is just stating which one is having the largest contribution on that final answer. All right, this last one right here, something a little bit different here in this one. So this one says, according to the U.S. Census, of all U.S. residents age 20 and older, 19.1% are in their 20s, 21.5% are in their 30s, 21.1% are in their 40s, 15.5% are in their 50s, and 22.8% are 60 and older. The table below shows the age distribution for a sample of U.S. residents aged 20 and older. Members of the sample were chosen by randomly dialing landline telephones. Then this says, do these data provide convincing evidence that the age distribution of people who answer landline telephone surveys is not the same as the age distribution of all U.S. residents? So this one is not saying anything about them being uniform. So I'm not trying to check if these are equal to each other. I want to know if they're equal to these percentages up here. Okay, so it's a little different from the last one. There's 2 ways that you could write out that HO and HA. So one way you can do it is you can do it like this. So you could say the proportion of 20 to 29-year-olds is supposed to be that value. 30 to 39-year-olds, that value. 40 to 49-year-olds, that value. And so on, okay? And then up here I'm just defining, so P and then that number is the true proportion who answer the landline telephone surveyed in that age group. And my HA says at least one is different, okay? The other way you could do it is I could write it out like this. So the age distribution of people who answer landline telephone survey is the same as the age distribution of all U.S. residents. And then the alternative would say that it's not the same, all right? Again, I didn't write everything out. I picked a significance level up here because they don't give me one here in this problem. This is a goodness of fit test. It does state that it's random. All right, to find these expected counts, you can't just take the total and divide it by 5. I have to take the total and multiply it by that first number. So I'm going to take that 0.191 times my total. And I get 200. So that's my first expected count. And I just wrote down, I'm just going to list the expected counts. I'm not showing the math for everything. This is just a small piece of this larger problem here. So then the next one, I would take the next percentage, the 0.215, or the 21.5%. So I'm taking the 0.215 and I'm going to multiply that by the total. All right, and then I'm going to keep doing that so I have all my expected counts here. Again, remember, they don't have to be whole numbers. They're just expected counts. All of those are at least 5. This one is a sample, so I'm checking my 10% rule here. And then again here on this one, so depending on how you do it, so if I was here in my list, so I've got my 141, my 186, my 224, my 211, my 286, and then in the next one, I've got my expected ones. So I got my 0.191 times the 1048, 0.215 times the 1048, 0.211 times the 1048, 0.155 times the 1048, 0.228 times the 1048. And then if I go to stat calc, or stat test, sorry, and then I go to that GOF test, this case the degrees of freedom are 4 because there's 5 categories up here. So I get that 48.17 and I get a pretty small p-value. And then if I look at my contribution, so my contribution is telling me which one is making that number so big. So there's a couple of them that are kind of large here. But you can see that first one was 17. And then that fourth one is kind of large here. But here, so I can say the p-value is less than alpha. So I can reject HO. There is enough evidence to say the age distribution of those who answer the landline surveys is different from the U.S. adult population. And again, if I was doing a follow-up analysis, I could just say the first age group contributes the most. All right, that's it for goodness of fit. I mean, I will say that in AP Bio, you might do it a little bit differently. This is how the statistician does it. The AP biologist does it a little bit differently. Okay.